All right, hello everyone. My name is João Carneiro. I'm a graduate research assistant at the University of Colorado Boulder, and I'm going to be presenting on Effector dynamics for sequentially rotating rigid body spacecraft components. And before I begin, I'd just like to acknowledge and thank my co-authors, Dr. Cody Allard, he's a GNC engineer at LASP, and my advisor, Dr. Hans-Peter Schaub. I'd like to start off this presentation with a question, which is how do we derive the equations of motion of spacecraft with rotating components or effectors, as we might call it. I call them. And I'm going to answer this question by giving a few examples. So the first example is this spacecraft, generic spacecraft. It has a rigid hub in gray, and attached to that rigid hub, it has a dual hinged panel, right, in blue. Now, to get to these equations of motion, we first need to define the problem, and to do that, we define some frames. You know, the hub has its own body frame B, and has its center of mass BC. And then we also define some hinge frames. We here assume that the spin axis are parallel, so basically the hinges are parallel to each other. We also assume that the center of mass of the panels are located at the geometric center of mass of the panels, and so we make these assumptions. These are reasonable assumptions, and they're actually quite useful in making some of the equations simpler because some of those terms just vanish. But we take those assumptions, and when we go through the derivations of the equations of motion, we go to the translation equation of motion, the rotational equation of motion, and then obviously additional equations of motion for each of the angles. And what we get is at the end a set of equations differential equations that define the behavior of this spacecraft with this particular component, which is a dual hinge, right? So that's the first example. The second example is a spacecraft, generic spacecraft, with a CMG, or a control moment gyroscope. Now, these CMGs are actually quite important. They can be used to control the attitude of the spacecraft. But from a dynamics perspective, they are composed of a structural frame. And inside that frame, there is a disc or a flywheel that spins, right? And then we can apply torque to that frame, so we can rotate the frame. And as we do so, we imprint a torque on the system, and then we control the attitude that way. But from a dynamic standpoint, you know, if we want to derive the equations of motion, again, we need to make some assumptions. We need to put the frames in the right place. In this case, the G frame, the structural frame. You know, the axis, one of the axes points towards the flywheel. As for the flywheel frame, it's located at the geometric center of mass of the wheel, and one of the unit vectors is the span axis. And actually, this formulation is quite complete because there's a lot of scalar offsets that we can define. But yeah, so after we make those assumptions, we go through the exact same process, and we define the translation, rotation, and the effector equations of motion, right? And then what we get is, again, a set of equations of motion for a spacecraft with this particular component. Now, as you can see, we have taken sort of the same procedure for both of these scenarios, but we have arrived at two different formulations because of the assumptions that we initially used, right? And so the question really is there a more general way to go about this? Because from a dynamic standpoint, both these components are identical. They're composed of two rigid bodies, each of them rotating about a single hinge, right? But because of the assumptions that we make at the beginning, what happens is the final set of equations that we get are specific to each of the components. And so previous work tackled this generality question. So yes, we can make it we can do this in a more general way. And the idea is we have this problem. This is the problem statement. It's just a generic spacecraft, again, with the rigid hub to where we attach a couple of rotating rigid bodies. And the idea is, instead of making the assumptions at the beginning, we don't. We just keep everything very general. You know, the frames, the frame for each of the spinning bodies can be anywhere. It doesn't have to be aligned with the body's principal axis. The spin axis doesn't have to be one of the frame's unit vectors. The center of mass can be anywhere. This inertia matrix can be diagonal. So making everything very general, and then going through the exact same process of deriving the translation equation of motion, the rotational equation of motion, and then the equation for each of the spinners, right? And what we get at the end is a completely general set of equations that describe a spacecraft with two rotating rigid body attached to it. And then after that, we can make the appropriate assumptions and use the same generic formulation to describe, the dual hinge solar panel or a CMG, right? Now, obviously, this is very powerful. For example, we don't have to validate the two different sets of equations of motion. We just have to validate one and implement that in software once. And neatly, the lower body actually doesn't have any mass or inertia. If we set those to 0, what happens is that the component is only composed of one rigid body, but that rotates along two, so it has two sequential rotations instead of just one. So that previous work that has been tackled, this will be tackled by previous work. And the question for this paper is, can we take that and not be constrained by just 1 or 2 degrees of freedom? As spacecraft have become more complex, there's been a lot of interest in robotic arms, for example, and those robotic arms are quite complex, chain of links. And the joints that connect those links are sometimes have 1 or more degrees of freedom. And so it's a really important problem. And it's very important to solve it in a general way, right? And so that's the focus of this paper. That's the focus of this work. And we start with the similar problem statement. Again, here we have a rigid hub, but instead of just 2 bodies, we have a chain of rotating rigid bodies. And again, some of these might not have any mass or inertia if we want to make a few sequential rotations instead of just one. But the idea is the same, right? We don't make any assumptions on the mass distributions, and then we go and derive the translation rotation and the effector equations of motion. So for this, I'm going to be talking a little bit about the approach. And for this work, we actually use Kaynes' method. Now, this Kaynes method is just a different dynamics formulation, as opposed to, for example, Newtonian or Eulerian mechanics, or even Lagrangian mechanics. It's just a different formulation. And while for the single and dual degree of freedom work, we actually use Newton and Eulerian equations, for this we use Kaynes' equation because it is a very systematic approach to finding dynamics. And because the goal of this work really is to find patterns, to go from 1 degree of freedom to 2 and n, right? That systematic approach is really beneficial for us. So I'm just going to be giving a brief overview of Kaynes' method. So first we find the generalized coordinate and velocity vector, q and u, respectively. As you can see, here we have the position state, the attitude state, and we also have each of the angles, the n angles. Then we need to compute the velocities and angular velocities of each body and make sure to actually find a pattern for the ith body velocity and angular velocity. Then we calculate the partial velocity table to find these properties VRI and omega RI. So V is the translation partial velocity, and omega is the rotational angular velocity of the ith body with respect to the rth degree of freedom, right? And now these are used to find the active and inertia forces for each of the rth degrees of freedom. And as you can see, F of R is the active force, F of R star is the inertia force, and you can think of F of R as being related to forces and torques, whereas F of R star is more related to mass times acceleration, or that typical Euler equation of I omega dot is or plus omega cross I omega, right? And then what we do is we apply Kaynes' equation after we find these active and inertia forces, and the Kaynes' equation just tells us that F of R plus F of R star is equal to 0, right? So we have the tools to derive the equations of motion. Let's do that. And so here the trick again really is to find those patterns. So we start off with the translation equations of motion. That knocks down 3 degrees of freedom. The rotation equations of motion, the equation of motion also knocks down 3 degrees of freedom. And then we need an effector or spinor equations of motion for each of the degrees of freedom. And so if we have a chain of n bodies, then we need n equations to solve for those n degrees of freedom. And this table just shows what our state variables are, the associated degrees of freedom, and what equation of motion solve for those. Now, this is perhaps overly simplified. all the translation, the rotation, and the spin equations of motion are very highly coupled, and so we can't just solve for one variable right off the bat. And to actually solve for these, or or at least expose the second order time derivatives explicitly, we write the equations in a modular form, right? So after you get the equations, you can massage the terms a little bit, and if we fit them into this modular form, we can actually get the equations of motion for example, instead of just one spacecraft with one link, it can have multiple links, or for example, it have a chain of links and a couple CMGs or a couple of panels. And the method we use for this is called the back substitution method. And it really deserves its own explanation. So that's what I'm going to do now. And so the back substitution method is just a way of writing dynamics to get that modularity. So for the translation equations of motion, as you can see on the left-hand side, we put all the explicit second order time derivatives. So that would be the linear acceleration r double dot bn, the angular acceleration omega dot bn, and then we have this big summation on the effectors and on the degrees of freedom on alpha double dot ij. Those are the degrees of freedom associated with each of the angles, right? On the right side, for the translation, we have forces and we have, transport theorem terms. That's pretty common. For the rotation, it's similar. Again, on the left side, we have the explicit second order terms, and on the right side, we have torques, gyroscopic terms, that sort of thing. Finally, for each of the effectors, we have the effector equations of motion. Now we can write them as an alpha double dot is equal to, or in terms of r double dot bn and omega dot bn. And this is really powerful because we can then back substitute this result onto the rotation and the translation equations of motion, right? Take A alpha and B alpha, plug them into the appropriate position and angular acceleration terms. And what happens is that the translation and the rotation terms all of a sudden are decoupled explicitly from the alpha double dot terms. And so what you get is you can write the equation, the translation and rotation equation in terms of this A, B, C, and D matrices. And you can actually explicitly solve for omega dot bn and r double dot bn terms. Once you solve for these, you can then put them back into the effector equation of motion into alpha double dot. And that's how you then take those equations and propagate them numerically. And that's how you get the time history for these systems. So that's a very powerful, really neat result. Now you might be thinking, okay, well, you've derived these equations of motion. How do you actually know that they're right? And this is actually a step that we still need to do for this work. But I'm just going to explain what the process is, and I'm going to show an example of what we expect to see. So because we are simulating physical components in a physical environment, we know that they must abide to physical laws. So in a conservative environment, or in an environment where conservative forces and torques are present, we know that energy and angular momentum must be conserved. And in fact, the rotational energy and angular momentum and the orbital energy and angular momentum must be conserved, right? And so what we do is we compute those terms, we run a simulation, and then we check at each time step what the relative difference is between that time step and the result at T naught, right? And so again, we haven't done this for this work. This is still to do, but I'm just going to show what we expect to see. This is actually pulled from the single and dual axis work that we did. So here are the expected results. As you can see, they're constant. That I'll just they might not look very constant, but as you can see, on the y-axis, that is 10 to the minus 14. So that is purely numeric error. And actually, this random walk is quite common of fixed time step integrators. But as you can see, here are the orbital angular momentum and orbital energy. They're being conserved, and so are the rotational energy, angular momentum and rotational energy components. So again, we haven't done this. This is still to do, but this is what we expect to see, and it's what we're going to be working to find. So to conclude, previous work has solved this generalization problem, particularly for single and dual axis components that are attached to a rigid hub. And what this work does is just expands on it and doesn't constrain itself to just 1 or 2 degrees of freedom. We can actually n degree of freedom length or chain of rigid bodies. And as I mentioned before, the equations still need to be validated using the energy and angular momentum conservation laws. That's our highest priority. So with that, thank you for watching.